As another example now, thinking about entropy through this lens of optimal encoding, let's say we want to communicate the result of a horse race, and let's say we have 4 horses. We want to ask how many bits do we need to encode each outcome. We can think about that on average, or we can think about each specific outcome of the race. Obviously there we want to use the Shannon entropy to talk about the number of bits to encode the outcomes on average, and the Shannon information content to talk about the number of bits to encode each potential outcome. To answer the question though, obviously we need to know what the probability distribution function is for our outcomes. To address this simply, we could start by assuming that each outcome is equally likely and has a 1/4 chance here. That's an easy one to do. This gives us 2 bits for each outcome. Whichever the outcome is, we know we need 2 bits to encode it, and therefore 2 bits on average. And we could assign those bits any way we want. We could encode A with 0, 0, B with 0, 1, C with 1, 0, and D with 1, 1. Or we can swap those around. As long as they are distinct encodings, it doesn't really matter. Now this probability distribution function here is obviously a maximum entropy distribution function. Whenever our outcomes are equally likely, that gives us the maximum possible entry across that many realizations. But there could be other distributions that the winners have. We could have a skewed distribution where horse A has a 50% chance of winning, horse B has a 25% chance, and horse C and D only have a 1 in 8 chance each. So how should we encode those values? Should we still use the same encodings, 0, 0, 0, 1, 1, 0, and 1, 1? Will that still be efficient under this probability distribution function? I hope you can see that the answer is no. If we use the Shannon information content here, it gives us different answers. It tells us that the most efficient coding scheme will use 1 bit for A now, maybe a 0, 2 bits for a B, say a 1, 0, and 3 bits each for C and D, say 1, 1, 0 and 1, 1, 1. This is obviously very different to using 2 bits for each of the outcomes, and it's different specifically because the probability distribution function is different here. With a different probability distribution function, there is a more efficient coding scheme to use than 2 bits for each outcome. We can find the encoding scheme that we should use using an approach called Huffman coding. This is a little bit out of scope for us, but I'll talk you through it briefly. You can read more about this in the text if you wish. Basically what we do is we line up our outcomes in order from most to least probable. And we can think about what we're trying to do here is to determine a coding tree, so that as we go down the tree, each entry further along the tree has a common prefix that's kind of denoted at a specific node that we're at. To work out what the tree should look like, what we do is we start with our ordered symbols and we group the 2 with the lowest probability. So here we would group symbols C and D, and that's what we do here. When I say group, what I mean is they have a node each, and then we group them underneath one common node. Okay, so C and D are now grouped under one common node. And we group their probabilities together too. So the common node here now has a probability of being reached equal to the sum of C and D. So this node here now has a combined probability of 0.25. And we replace C and D in our list with this combined node with the probability 0.25. So then we're going to group that combined node with the node for B. And that's what happens here. We combine these two, which were now the 2 lowest probability items in our list. We combine them under a new node, and that new node now has a combined probability of 0.5. So then our list only has a probability of A of 0.5 and our combined node with a probability of 0.5, and we combine them again, and that finishes our construction of the Huffman code. So what we have now is a tree, and we can see that we're left with each node in the tree, and all we do as we go down the tree at each split, we write a 0 and a 1 randomly. It doesn't really matter which way we do it, but a 0 or 1 on each node, so long as we have a 0 and a 1 here, the same as we go down here again, and the same as we go down here again. Then we can read off the code for any given symbol by starting at the top of the tree and reading reading the digits off as we go down. So C is a 1, 1, 0. So that tells us how to encode the bits. Let's say we're receiving the bits then. As we receive the bits, we traverse down the tree with those bits. So here, if a 0 comes in, we come down here and we're done. So it's an A. If we receive a 1, we come down here. Let's say we receive a 1 next again, and then another 1. And we terminate, and that tells us that sequence of 1s informed us that there was a D. What's important about Huffman code is that there are no symbols have a coding and encoding, which is the prefix of another symbol. So receiving a 1, 1 is not a finished sequence. There is no symbol which is listed here against 1, 1. The reason we do that is so that we don't have to waste bits on saying that we're finished. Otherwise, if we did have a symbol here, we wouldn't know if are we finished, or are we waiting for another 1 or a 0 to know if it's a C or a D. So we don't do that. There are no codes that are prefixes of other codes here, and that's the maximally efficient way to do it, to keep sending our symbols to keep sending encodings of our symbols one after another. So in this case here, for these probability distribution values, we get an average code length, an average Shannon entropy of 1.75 bits. And we can see then by using the actual probability distribution function that we had leads to a more efficient coding than if we just assumed 2 bits for every symbol. Okay, we can see there's less bits here to encode in this most efficient way than if we just guessed 2 bits in general. Importantly also, information is not about meaning. Okay? We have completely decoupled the meaning of the number of bits for each symbol and the code that we use from what it actually means. A horse B might mean something very, very greatly to its owners. It might mean something very greatly to the person that bet on it. We have completely decoupled the meaning from the number of bits and from the values here. Okay? That's important. Information theory is semantic free. Let's have a look at one more example here, which is thinking about encoding letters in English language text. So we ask the question, can we get any insight into how many bits to use for each letter? Now I've put a footnote here to say determining the coding is effectively out of scope for us. I've just told you a little bit about that with Huffman code, but that's as far as we'll go on that. But let's see, can we get any insights on how many bits to use for each letter? For this, we can turn to table 2.9 in Mackay, where he lists for all the letters of the alphabet, and including a space, what the probabilities of those symbols are in some sample text. I'm not sure where he got it from, but let's trust him that these probabilities are correct in the sample he was looking at. And then all we've got to do is convert those probabilities for each letter and space into the Shannon information content. As we know, the Shannon information content tells us the number of bits we would use to encode those symbols in a code that is maximally efficient on average, so which uses the minimum code length on average across all of our symbols. And we can see there by scanning through, we can see which letters stand out as using a lot of bits. Well, we see J does, and so does Q. And that makes sense because they are the least used letters here. So we push a lot of our code into those least used letters, so we can save a lot of code on our most used letters. Like we can see E now only requires 3.5 bits and a space only requires 2.4 bits. And by doing that and averaging, taking expectation value across all our symbols, we're looking at 4.1 bits on average to use. And that is less bits than we would use if we assumed all our symbols were equiprobable. With 27 symbols here, that's going to require almost 5 bits on average if we use an equiprobable distribution. So we're saving bits by looking at the real probabilities of our symbols. You might ask then, what's the meaning of the non-integer number of bits that we can see in the table here? So obviously that comes straight from the Shannon information content, but how can we actually achieve that? How can we do an encoding to achieve those minimal lengths? Otherwise, we might have to go to the ceiling of each number of bits. We might have to go to 5 bits for A, 7 bits for B, and so on. How can we actually get close to this minimum number of bits? the answer is that we encode our digits not just one digit at a time. If we do one digit at a time, well then yes, we have to use an integer number of bits being the ceiling on these values. We can use block coding by encoding multiple samples together. So we could code a pair or 3 letters together, and that will allow us to save bits. So say for example we coded an A, B and C together if they occurred in sequence using one particular bit sequence, and we can see if we do that then we're going to add all these together, and that adding those together may be less bits than if we took a ceiling for each symbol on their own. So that's how we get to those smaller number of bits using what we call a block coding. Again, that's a little bit out of context, but I just wanted to mention it here for you. Importantly, we can still do better if we look at the entropy of these blocks. So if instead of, say we got this sequence of A, B, and C, and we think of a code across those, what we can do is actually look at the probability of getting those doubles or triplets together, and that will allow us to do something more efficient again. And that's what we'll look at in our next little short video vignette.